Okay, thank you everybody for attending my talk. And my name is Fabio Falzoi. I work as a senior software engineer at Develer. It is a company based in Florence. And I have experience with various languages, and lately I'm using Go. And I would like to talk a little bit about Go garbage collection. Okay, the roadmap of the talk. First of all, we will introduce the memory management in Go. Then we will reason about the basics of Go garbage collection and also the inner details. And after that, we'll briefly see how the GC impacted the performance of your application. Okay, let's start from the memory allocator. Unlike other languages, the Go compiler uses escape analysis to decide where to allocate objects on the stack or on the heap. And stack allocations are preferred because they are considered to be cheaper, but to do a stack allocation, you need to know in advance at compile time the size and the lifetime of your objects. And since escape analysis rules are not part of Go language specifications, you shouldn't try to guess, but you should use this command to ask the compiler why and where it is allocated on the stack or on the heap. Let's see this with an example. Okay, consider this code snippet, and here I'm just a function to allocate an object. And if I ask you where this object will be allocated, well, the correct answer is it depends, because if I use this code snippet in this way, since this function is being inlined and the address of the newly allocated object does not escape the f function, this will generate a stack allocations, and you can see that from the last line of the escape analysis output over there. But if you use the same code for allocating the object, and here the address of the object has been stored to top-level variables, the address of the object escapes the f function, and so the compiler needs to generate a heap allocation. And I think there is a talk on the other track about all the details about inlining, escape analysis, and GC if you were curious about these kind of things. Well, speaking about stack allocations, stacks are managed in frames. A frame is just a memory space for a function call. And when you create a new frame, or when you reclaim a new frame after a function execution, you have to modify just a single register in your CPU, the stack pointer register. Let's see an example for these two. Here we are in the main function, and as you can see over there, in our Go routine user stack, we have already allocated a frame for the main function, where the x variable is allocated, and the line over there is the graphical representation of the stack pointer register. All the memory that is beyond that line is considered not to be valid. When the f function is called, we generate a new frame, and this is done because I marked that function as no inline, forcing the compiler to generate a full-fledged Go function call. So a new frame is allocated for that function, y is allocated there, and as you can see, the line of the memory valid is moved because the stack pointer register is updated. When we return from the function, that frame is logically deleted. It is not zeroed, but the stack pointer is updated, and so that memory ends up as being not valid. Okay, so user stacks in Go starts at just 2 kilobytes on x86-64 architecture. And this is crucial because in your Go application you can have a lot of Go routines. So one of the reasons why Go routines are really cheaper than normal kernel threads are the fact that they start with just 2 kilobyte stacks. But they can grow dynamically, and they can grow up to 1 gigabyte on AMD 64 architecture, so they are practically infinite. And okay, there is a process that is called stack split, that when a function is called, the compiler emits a prolog for that function, and in that prolog, the remaining room for the stack is verified, and if it isn't enough, A new stack is allocated, new memory for stack is allocated, specifically the size is doubled, and to keep the stack contiguous, all the stack is moved in the new region of memory, clearly adjusting the pointer to the stack allocated objects. And there is also the opposite process. When the memory that you are using for your goroutine stack is less than 25% of the allocated memory, the Go runtime will shrink the stack, again moving the stack in the new memory if needed. And this couple of operations have a cost of big O of 1 amortized, since here we are halving the size of the stack. Okay. Goroutine user stacks can grow dynamically, so we should ask ourselves where all of the memory for goroutine user stacks comes from. It turns out that memory for goroutine stacks come from the Go heap. And for stack allocations less than 32 kilobyte, we have a local cache, a cache for each processor to avoid locking and so contention in the common case. But if that cache is empty, or if you're trying to allocate a room for a stack that is greater than 32 kilobyte, you have to rely on a global. Sorry. Okay, sorry, can you hear me? No. Can you hear me now? No? Okay, it is, okay. I won't talk about the stack anymore if you, if this is the result. Okay, by the way, and okay, if you're trying to allocate a stack that is greater or equal to 32 kilobyte, you have to rely on a global pool, and so you have to take a look, and here there may be some problem of contention. But anyway, stop talking about the stack since the results are quite strange. Let's talk about the heap. First of all, we have to say that the Go heap is logically divided into spans. A span is a run of contiguous pages where objects of the same size are allocated. The Go Memory Allocator defines 67 different size classes. So when you allocate an object, you have to stick to those sides. And here you can see an example of just one size. Regarding the heap allocation paths, we have quite a similar path to stack allocations, because for each virtual processor, you have a local cache where you can take memory for allocations. And this is done, again, to reduce contention in the common case between the various goroutines. And the interesting things to note here is that for each size class, there are two spans, the no-scan span and the scan span. The no-scan span is like an optimization where the object that does not contain pointer are stored, and we will see after why this is done. Okay, again, if those caches are empty, you will have to rely on a global heap structure that manages all the Go heap, and if even that structure does not have enough memory for your allocations, the runtime will ask more memory to the kernel. Okay, if you think a little bit about what I've said regarding stack allocation pattern and heap allocation patterns, you can see that they are quite similar, because we have caches for the normal cases. And the main point is that since they are similar, why stack allocation should be considered cheaper than heap allocations? And the main point is that the difference is not the allocation cost, is the deallocation cost. Because as we saw with the stack, when we have to reclaim a frame, we simply have to adjust the value of a CPU register. But for heap allocated object, to reclaim memory, we have to rely on garbage collection. So before speaking about garbage collection, one who should ask ourselves, well, should I give up writing Go if I'm looking for a high-performance language? In my opinion, no, and likely I'm not alone, it seems. And this is first because garbage collection is very useful to prevent an entire class of memory errors, especially memory leaks, that are, first of all, really hard to debug, and after that, they can easily lead to an out-of-memory error that are, for your web services, probably this is not what you want. And besides, as we will see, Go garbage collection is really optimized for very low latency with a reduced impact on throughput. Okay, so let's see the inner details of Go garbage collection. First of all, we start from the basics. The basics algorithm for Go garbage collection is mark and sweep algorithm. It is a simple algorithm divided in two phases. The first one is the mark phase, where you start from the roots, looking for addresses of heap allocated objects. When I talk about roots, I mean global variables, Go routine user stacks, addresses on BSS and data section, and so on. And traversing the heap graph, you mark each object that is reachable. You mark it as alive since it is reachable by your user code. After that, there is the sweep phase. In this phase, you check each allocated object, and if it is not reachable, if it has not been marked, you simply can reclaim that memory. Simple as that. A nice way to reason about the mark and sweep algorithm is to use the tricolor abstraction. The tricolor abstraction is a way to color the objects during the marking phase to understand their status. Initially, all the objects start as white because they are not marked. When we reach an object for the first time, we consider it to be gray. And when all of the reference of the objects has been reached, we consider the object to be black. And at the end of this process, you can see here a picture of this. At the end of this process, we will end up having just two sets. The white set is the set containing the objects that are garbage that you want to reclaim, and the black set are the objects that are still in use by your application. One thing that is really important to say is that we can't have a direct pointer from a black object to a white one. And this is because the black object is an object that is still reachable by your code. You still hold an address for that. And if you can reach a white object through that direct pointer, this means that that object can't be white, simply because that object is still reachable. So in other words, if your garbage collection is correct, the strong tricolor invariant must hold true. No direct pointer from black object to white object. Okay, and here you can see a representation of classical stop-the-word mark and sweep. And it is a very simple algorithm, and also it is very easy to control the growth of the heap, because when you need memory, you stop your application and you launch the garbage collection to reclaim memory. Unfortunately, there are a couple of problems. The first one is the external fragmentation, because as long as you reclaim objects from the heap can become quite fragmented. But we already see how Go try to mitigate those issues, and Go uses size classes free lists, as I said before. But the main problem is the latency inflicted to your application, because when the garbage collector kicks in, the word is stopped. And in GC jargon, this means that the thread of your application, the Mutator threads, are completely stopped. Your application is not making any progress. And since modern memory is not limited by capacity, but is limited by latency, this is a real problem for modern application. So let's try to understand how Go addresses this. To improve the latencies of garbage collection, one way is to do a concurrent garbage collection. So you mark your objects while your code is still executing without stopping it. And this is what Go does from version 1.5. But if you think about the phases of garbage collection, with the sweep phase, we have no problems, because since the objects are unreachable, during the sweep phase, I'm just messing with the objects that are unreachable. And so it is safe to concurrently reclaim that memory, because our application can't reach those objects. But regarding the marking phase, things are a little bit complicated. Let's see an example. Okay, suppose that in a certain moment of time, your application has this memory graph. Clearly, it is overly simplified, but well, it's just an example. And your garbage collector is marking the object, and it is arrived at a point that you can see over there. And now suppose that we are trying to concurrently execute this code here. What we are trying to do is simply move the pointer to the, we are deleting the pointer from C to E and moving that from the D object to the F object. But if I do that, the problem is that now I have a direct pointer from a black object to a white object. So at the end of the garbage collection, the F object will be incorrectly reclaimed. So this way, in other words, the tricolor invariant does not hold true anymore if we don't do anything clearly. Okay, so what should we do? What should the Go runtime do to guarantee the correctness of garbage collection? We need a way to inform the collector that our application is concurrently mutating the heap memory graph while the collector is marking. And the way to do so is changing the normal operation that you do with your pointers, like write, read, and so on, with a kind of barrier. You can think about the barrier as a function that, besides, in this case, storing the pointer, the barrier does something else. And we will see in a minute what it does. Okay. Until Go 1.7, Go used this kind of barrier. This is, first of all, this is a write barrier. Why a write barrier, not a read barrier? Think about typical non-contiguous data structures like linked lists, trees, and so on. And think about typical operations on them, like search, insert, remove, and so on. You will soon realize that the number of pointer reads is far greater than the number of pointer writes. So if you want to lower the overhead of the barrier, it is better to choose a write barrier. And this kind of write barrier is a Dijkstra write barrier. It simply shades the object pointed to by PTR when you are assigning that object. If we recall the object, the example from before, this is the write barrier in action. When we simply copy, the pointer to the F object gets shaded as gray. Okay, so pro and cons of this kind of barrier. First of all, it ensures the strong tricolor invariant, so it ensures the correctness of our garbage collection, and also it helps us with making progress toward the end of the marking phase, because it helps us in marking other objects. But there is a problem. Think about addresses of heap allocated objects that are stored in GoRoutine stack. Clearly, you need the write barrier. You need to protect those addresses even if they are on the stack, because they are pointing to heap objects. And we said that normal Go application can have a lot of GoRoutines, so we have really a lot of GoRoutine user stacks. And using a write stack barrier is too much of a overhead. So the Go team decided to use another approach that is called perma-grade stacks. Simply put, the perma-grade stacks means that you can concurrently scan the stack during the marking phase, but at the end of the marking phase, again, you need to stop the word and to rescan again all the GoRoutine user stacks that has changed. This is a problem because doing this way, you are introducing potentially unbounded latency in your application, because if you have a lot of GoRoutines, the end of the marking phase that you can see over there in that stop the word phase does not have a bound on his length. And okay, so how the Go team decided to resolve this problem, to address this issue? They switched the type of barrier using an hybrid write barrier, starting from Go 1.8, if I can recall it right. And here is the algorithmic implementation of the barrier. We won't dig too much into details because it is quite complicated from a theoretical point of view, but what is important now is that the hybrid write barrier combines two kinds of barrier that, taken alone, needs either a rescanning of the stacks at the end of marking or a stack snapshot at the beginning of marking. But if you combine them, you can concurrently stack scanning without a stack write barrier and without rescanning the stack with the word stopped. So this is maybe it is the main piece of the garbage collection in Go, the most important piece of garbage collection in Go. But it is not enough. In Go 1.10, they decided to improve the implementation of this barrier. So despite being the same algorithm as before, the implementation of the buffered write barrier has been introduced, and here you can see the implementation in the Go runtime over there. Simply put, they introduced a buffer for each P virtual processor, where we store the address of the object that needs to be shaded, and if there is enough room on the buffer, the fast path of this buffered write barrier takes place, because the barrier is implemented in assembly, and doing so, you have to save and restore just a couple of registers, not the entire CPU register. So in the first case, the fast path, this is not a normal Go function call. It is way faster than a normal function call. When the buffer is full, then you have to rely on the slow path. So all of the objects in the buffer of the addresses need to be flushed and graded as usual with the barrier I talked about before. And in this way, you need to save and restore a lot of CPU registers. So this is similar to a normal Go function call, but it is executed only if the buffer is full. Okay, so let's dig a little bit inside the details of marking in the Go runtime. Sorry. First of all, Go reserves 25% of the available CPUs for background marking. So the CPUs are reserved for marking jobs. Since a normal, usual machine, even mine that is quite a little bit old, has 8 CPUs, so 25% means two CPUs. This means that we have more than one Go routine that is concurrently doing marking. And so we have to be worried about contention and locking. And to address this, inside the runtime, we have a distributed work pool. So the marking work is distributed in a pool. We have a global buffer and a local buffer, a buffer for each P virtual processor. And a gray object is considered so when it is marked and it is in one of the queue, either the global one or one of the local queue. Instead, an object is considered to be black when it is already marked and is already outside of the queue. Okay, so since 25% of the CPUs are reserved for marking, what happens if there are one or more Go routines that is allocating very heavily? It is allocating a lot of memory. If we don't do nothing, we can end up with that Go routine outrunning the garbage collection marking work. And to avoid that, at the start of the garbage collection cycle, the runtime enables a mechanism called mark assist. Mark assist is a budget system where each Go routine that does some marking job earns credit, and when a Go routine instead is requesting an allocation, it is charged based on the size of the allocation. When a Go routine tries to allocate an object, but its budget is already exhausted, it has no credits, first it tries to steal from another Go routine, but if it can't do that, the Go routine is stopped and is forced to do marking job. And this is a way to slow down the allocation rate of our application during the marking phase. Okay, so since we saw that garbage collection is a distributed process in Go, we need a distributing algorithm to check if we are at the end of the marking work. So when a Go routine detects that it has no more jobs on the local work queue, it tries to acquire semaphore, then it tries to check the global work queue, and if there is no more work to do, for each other P virtual processor, we try to flush first the write barrier, the buffered write barrier, and then the local work queue. If there are no more work to do, okay, we are done. The marking phase is ended, and so we can switch to the mark termination phase but you can see that this algorithm can fail repeatedly to detect the end of the marking phase. But this is not waste time, because doing so, flushing all the local works to the global queue is a way to rebalance the work between the global work pool implementation. It is something similar that is done with work stealing in the Go routine, in the Go scheduler, if you think about it. Okay, so here is a graphical representation of all the phases of Go garbage collector. And the important thing to note here is that the marking phase is the bulk of the garbage collection, but the stop the work poses now are bounded, are limited, and are very short. This is because in this implementation, the stop the work poses are there mainly to activate the write barrier and the mark assist mechanisms. And the important thing is that now the poses are not proportional to the heap size anymore, clearly. So this is the main point of the Go garbage collection. Okay, so now we know quite a lot about Go garbage collection, but when should we start the next garbage collection cycle? Using GoGC environment variable, you can set the heap goal. Specifically, the runtime sets a heap goal to that formula. By default, GoGC is 100, and this means that starting from the size of the heap that is live at the end of the current collection, the goal for the next collection is set to the double of the size of that size. So the next collection will start so that the end of the marking phase will produce a size heap equal to the goal. This can sound quite complicated, but I will explain that in the next few slides. Recall for a minute the stop the word implementation of mark and sweep garbage collector. Setting a trigger, an heap trigger here, is very easy, because when you reach the heap goal that you calculated with the formula before, you simply need to stop your application and let the garbage collector kicks in to reclaim memory. But unfortunately here we are doing concurrent marking. In other words, while the garbage collector is marking, our application is still allocating objects, increasing the heap memory size. So here we have to set the heap size trigger, the point where the garbage collector starts the marking phase, a little bit earlier. And this is the job of the Dissipation algorithms. The Dissipation algorithms have to optimize in two ways. The first thing is to try to minimize the distance between the heap size goal and the effective heap size, that red area over there, because clearly you do not want to go over the heap size goal, because you don't want to risk an out-of-memory error, but you do not want to fall too short from the heap size goal, because if that red area is real long, that is, it means that you are garbage collecting too frequently. So you are utilizing too much CPU for garbage collection. And besides, you also don't want to use too low CPU, respecting the goal of 25% we talked about earlier, because if you use, if the garbage collection is too long, the problem is that your write barrier will be on for more time, and the mark assist will be on for more time, and this is bad for the throughput of your application. So the Dissipation is quite complicated, and he has to estimate the marking work based on the results of the previous collection, and also it has to estimate the allocation rate of your application. Okay, so let's talk a little bit about sweeping. Sweeping in Go is really fast, because for each span there is a couple of bitmaps that are kept to describe the span, and specifically we are interested in these two fields over there inside the runtime. Alloc bits tells us which object in a span is allocated, and GC mark bits tells us about which object in the span are already marked. So at the end of the marking phase, the objects in the span that are alive are the ones that are marked. So we simply need to assign the value of GC mark bit to alloc bits, and that is all it takes to sweep a span. So sweep is really fast, but the problem is that the marking phase is relying on this data, so we need to sweep all the spans before the next collection can start. So if we are late in sweeping all the span, we will end up delaying the collection and despite the Dissipation algorithm. So to do so, the approach to the sweeping for Go application is similar to that of marking. Just like we have proportional marking with Go routines dedicated to background marking and mark assist, here we have proportional sweeping. We have Go routines that do the background and concurrent sweeping when they are idle, and also we have lazy sweeping. So when a Go routine tries to allocate, if there are unswept span, the Go routines are asked to sweep the span. And the pacing of the sweeping rate is again decided by the Dissipation algorithm. Okay, so now that we know quite a lot about Go garbage collection, let's try to reason a little bit about the performance impact on your applications. First of all, a summary, and here you can see what garbage collection is doing, more or less. You can see that now we have two stop-the-word poses that are bounded. Inside the two stop-the-word poses, we have the marking phase with 104 virtual processor dedicated to background marking. And also over there, you can see the mark assist requested to Go routines that are allocating too heavily. And during the marking phase, the write barrier is always on. Outside the marking phase, the write barrier is off. And also, well, we have the impact of sweeping, but since, as I said, sweep is really fast, we can avoid considering sweeping for our reasoning. Okay. First of all, in 2018, Rick Alzo from the Go team gave a presentation about Go garbage collection, and they defined their service level objectives. And the important thing to note here is that they claimed to be able to reach stop the word poses less than 500 microseconds. And here you can see a quick test that I did with my machine that is even quite old. And garbage is a benchmark that is designed to stress the Go GC. It repeatedly parses a piece of Go code. And as you can see, the results are over there. The typical stop the word poses are about tens of microseconds. And I think this is really impressive. And well, the Python guys over there don't have this kind of good garbage collection. So kudos for us gophers. Okay, and apart from that, there is regarding throughput, there is another thing to say. We already said that there is the write barrier and there is the mark assist mechanism that are inflicting an overhead to the throughput of our application, but also there is the problem of floating garbage. Now, suppose that at a certain point you'll end up with those two objects in the heap. The first one is already marked black, and the second one is marked as gray. Remember that your application is concurrently executing, so for some reason your application deletes that pointer. This clearly can happen, but since that pointer deletion happens during the marking phase, at the end of the marking phase, those B objects will be marked as black. So despite being garbage, that object won't be reclaimed. This is clearly not a problem of correctness of our Go garbage collection because we are not corrupting memory that is still in use. The problem is that we are doing more work than needed because those objects will be eventually reclaimed, but in the next garbage collection cycle. And so floating garbage together with mark assist and write barrier gives us a little bit of overhead to our application. Okay, first of all, if you care about performance, don't try to guess, just like escape analysis. You really need to measure the results of your application. And Go is really great in profiling and tracing. And to me, this is a nice tool to use. This is a curve that you can obtain from the GC tracer, and you know you can use the GC tracer even in production with minimal overhead. And the minimum mutator utilization curve describes the minimum utilization of your CPU by the mutator that is your application code. So if you look at that curve over there, more that curve is pushed to the right and pushed close to the x-axis, and the more your application is GC bound. And in that case, it is useful to try to improve the memory allocation rate of your application. Besides, this image is interesting because the y-intercept tells us immediately how much CPU utilization we spend for our program, and the x-intercept tells us the length of the maximum post time inflicted by our application from the garbage collector. Another tool that you can use to have very detailed information on each garbage collection cycle is the GC trace. And the format is quite complicated, but you have the complete description of the runtime package. What is important to note here is that you can have information about all the phases, and especially the stop-the-work phases I talked about before. And also you can have you can see the decision of the GC pacing algorithm over there regarding the heap size goal, the effective heap size, and so on. Okay, so you profiled your application. You verify that your application is experiencing GC pressure. So what can you do as a first thing? The point is that if you manage to reduce the allocations on the heap, there will be less marking work. And so we will have a shorter GC cycle, and the write barrier will be on for less time, and the same for the assist mechanism, and finally the same for floating garbage. We will have less floating garbage. So what can we do to reduce the heap allocations rate? Well, first of all, recall that the scanning time is roughly linear in the number of pointers scanned. This means that, first of all, you should use escape analysis and profiling to find where and why the runtime is allocating on the heap and why it is allocating so much. After that, I'm not saying here that you shouldn't use pointers, but sometimes it is better to copying values instead of passing pointer for a couple of reasons. First of all, because as we saw regarding garbage collection, the marking phase means to traverse the entire memory graph. So if you have a lot of pointers, you will have a longer traversing time. But besides, pointers are not good for caches because they have poor locality of references. So you can experience even also some problems with your caches. If you can, you should try to refactor your type in your performance critical path to avoid pointers and try to benchmark the results. As an example, the time struct has a pointer inside for localization. So if you're doing a lot of if you're doing some kind of logging and taking some form of timestamp in your performance critical path of the application, maybe it is better not to use this kind of structure, but maybe use some kind of timestamp that can be stored in a int64 variable and so on, maybe translating that later when you need to visualize the time. Clearly, this is just a suggestion. There are a lot of cases to be addressed. Another thing that you can do, this is a kind of micro-optimization, but you can try this, to be more sympathetic with the memory allocator, you can try to pack your struct, reordering the fields so that the memory alignment requirement end up in giving us a lower memory footprint for our struct. And you also have a web service to visualize how the runtime is constructing memory hour structure. And luckily, this is available only for AMD64 architecture, but I think, well, the most of the Go development happened there. And here you can see that with the same fields over there, I managed to reduce the occupation of each object from 80 bytes to 72 bytes. Kind of a micro-optimization here, but can be useful if you are allocating a lot of the same objects. Maybe what is more useful to do is trying to reduce the allocation rate, relying on sync.pool. Sync.pool is can be not so easy to use, but it has also been improved in Go 1.13. They have introduced a victim cache mechanism, so it will take a couple of garbage collection cycles to reclaim the objects that are in the pool. Remember that if an object is in the pool and the only reference to the object is in the pool, that object can be reclaimed at any time. But now we have this optimization, so we need 2 garbage collection cycles to reclaim that object. So if you are locating a lot of those kind of objects, this is a nice way to reuse them. Besides, the sync.pool is safe to access by multiple coroutines. Okay, so you try to improve your allocation rate, and what else can you do if you want even more performance, or if you're up to risk something more? Okay, you can try to tune the garbage collector. And unlike other garbage collectors like Java, I don't know so much about Java garbage collection, but what I know is that it is really customizable. It has a lot of options. Go exposes just one knob, GoGC. What does it mean to modify GoGC? If you increase GoGC, it means to trading memory for a better CPU utilizations. And you can also change at runtime too, despite it is not so useful, but you can try that for a very specific kind of application. And the problem is that if you increase too much GoGC, the heap grow becomes really harder to control, because here is what happens when your application is in steady state. In steady state means that the size of the live heap is quite similar from one collection to another. If at certain point your application has a spike in the live heap size, with GoGC equal 100, the spike in the heap goal calculated will be quite limited. But if you consider a higher GoGC, like here 300, you can see that the spike over there is really bigger. GoGC has this kind of amplification effect, if you can let me use this term. And if you think about even higher value for GoGC, like 1000 and so on, it can become quite difficult to control the heap, and you can end up having out-of-memory error. So be careful. Well, sometimes what you want to do is not to care. You don't care about the heap growth ratio, but you have kind of a fixed set of memory to use for your application, and you would like to say to the garbage collector, okay, I have this memory for the heap, you use as much as you want, and please try to increase the garbage collection frequency if we get close to that limit. Unfortunately, this is not possible at the time, but there is a proposal for extending the API of the garbage collector, with the introduction of this API set max heap, and so I think that we can have that in the near future, maybe in the next releases. And this maybe will be useful for a special class or application that has a small live heap, but a very high allocation rate. So for this application, normally they relies on having an high GoGC, but they will end up having the problem I said before. So. This is all I had, so thank you for your attention, and I'm done. I managed to... Okay.
Are we ready to questions?
Yeah.
Yeah? Okay.
If there are some questions, okay.
Thank you very much. Thank you very much for a very nice presentation. It was a very interesting talk. So I wanted to ask 2 questions and actually make one point about the struct layout. If you can point it to the slide, if you don't mind.
This one?
Yes. So I wanted to point out that in big structures, there's not only the benefit of reordering the struct to layout so you don't lose these bytes, but also to place the pointer in the front. Because for every struct, for every allocated object, GC runtime has a special structure that has bitmap that allows it to inspect it. And it shows that basically it has a bitmap that shows if current field is pointer and the next field is pointer 2.
that is called precise garbage collection. It is there since Go 1.3, I think.
Yes.
And I would like to talk about that, but I was out of time. So I removed the slide before submitting them.
Yeah, so it's most of the time it's unnoticeable, but sometimes it can reduce your garbage collection times.
Yeah.
And the next slide, if you don't mind.
See, in this case. Okay,
no, the one after the pools.
Ah, okay, pools. Okay, over there.
Yeah. This I wanted to tell everyone. There's a big problem with this if you don't control the pool growth. So what do I mean by this? Always check if your byte slice or int slice or any sort of slice increases over its lifetime. So for example, here you allocate 124 elements, but you can append it, you can change it, and if you put it back in the pool, check if it doesn't exceed some sort of arbitrary limit, for example, 65 kilobytes. Why it's important? Because big pools containing big objects can be very bad for your memory and overall performance of your application. So pools of small objects are very useful, but pools of big objects are not that useful. This is actually was that often in occurrence, so they actually added a note about that in the documentation of Go 1.14. So,
yeah,
sorry for...
No, I think this is very interesting. But by the way, I think another thing to say is if you look at Rick Hudson's presentation and other things he said, it is very interesting, is that Go allows internal pointer. So you have, if you have a very big structure and you have a pointer to one of the field inside the structure, this pointer will keep alive the entire structure. So yes. This is another kind of problem that you may face.
Yeah. So my question is, does GC consider pointers that point to the objects which do not escape? For example, we are passing the object, but escape analysis can prove that object does not escape. Does this object increase GC time spent in GC?
No, if the object doesn't escape,
object doesn't escape, but it's still passed by pointer, and it's still considered as pointer. Just the
no. In this case, no, because it is allocated on the heap. So you won't have problem because thanks to the precise garbage collection you were talking before, the Go runtime has information about the kind of pointer. So if it is a stack allocated pointer, you can see in runtime that it is simply skipped. So it won't increase the marking time. Well, it's just the check, but anyway, it is not a real overhead of the marking phase where you traverse an heap graph. So that's why pointers are not bad as such. They are bad if they lead to a lot of allocation in your performance critical path, because heap allocations are the one that will end up extending the length of the marking phase.
Thank you very much.
Welcome.
Okay, questions?
Thanks a lot. I have a much simpler question after that one. You've talked a lot about heap garbage collection, and what about stack? Is it a difference between Go versions starting from 1 point something till 1.13 in auto decisions what we go into store in heap and what in stack?
Okay, first of all, escape analysis is continually improved. So I think that in the next release, 1.14, escape analysis has again improved. So the decide which decision Go takes to allocate on the stack on the heap is they continually improved that. And specifically now, if I have time, this is the reason why Go doesn't use, as far as I know, at least a generational garbage collection, because short-lived objects lives primarily on the stack thanks to the efficiency of escape analysis. And besides, even the stack allocation path I showed here has undergone quite a bit of changes during the release. And I don't remember very well, but these contiguous stacks, I think, is there from 1.5 or 1.7. Before they tried something like segmented stack, I think they were trying to increase the size of the allocated memory for the stack, but the memory was fragmented. I don't remember that very well. By the way, if you search for difference between segmented stack and contiguous stack I presented, you will find the history of that.
Thanks.
Welcome.
Anyone else? Okay, thank you.
Welcome.
Applause.
Thank you.